I know I didn't ask how you guys are doing.
How are you doing, Judy?
I'm good. Thank you. I was waiting for someone to ask me how I'm doing.
Good to hear.
Okay. So, we are going to get started right now. And someone is trying to think maybe that's pre. Layla. Okay. I may need to download my presentation, I think. So now I have to ask everyone. Abigail, how are you doing? That's my presentation download.
I'm doing good. It's
Yeah.
been a week, but it's good.
Okay.
I didn't play much.
Tima, we already did your physical exam. Otherwise, are you doing okay? Tim, are you muted?
Yes, I am muted. Yeah, I was saying for one of my classes, we did a test on decision trees, and I was like,
Okay, you're really distant, so I can actually not hear you.
oh, I said, so one of my classes, we took a test on decision trees on
What?
Thursday. Yeah, so I was like,
Oh my God. Oh, wow, that's amazing.
So yes.
Elmira, how's studying going?
So studying is going not as great as last week, and because I have like so many stuff going on at work. But I did half marathon like right half an hour ago, so my brain is not working.
Oh, okay.
Wow, that's awesome.
Yeah.
Wow. Okay. Jeffrey, how are you doing?
I'm good. I just got an apple fritter from Revolution Donuts, so I'm in a great mood now.
Wow. I don't even know that there's Revolution Donuts in Atlanta.
We'll have to go there. It's their donuts are pretty good. Are
they like Voodoo Donuts in Portland? Because I mean, I've been in the home for real donuts, you know?
So it's funny you say that. My girlfriend used to work at Oregon Health Sciences, and I would say she does not think they're as good as Voodoo, but well, hold on.
They're better.
Oh, she thinks they're actually better. Never mind.
Oh, wow. Okay, we have to go there as a book club. Actually, so myself, Chima, Jeffrey, we should go out sometime socially distant, and then that would be cool. And get some donuts. Okay. Layla, how are you doing?
Please do that. Like I'll wave at you from Chicago.
We'll Zoom you guys.
Good.
Yeah, you're doing good?
Yeah, thank you.
Okay. Nazanin, welcome back. How are you doing?
Thanks, I'm fine.
Okay. And Sina, how are you doing?
Doing good. No complaints. Enjoying life. Kind of jealous about Jeff's donuts, but otherwise doing good.
Okay. Toby, how are you doing?
I'm doing well, although there has been protests here in Nigeria.
Oh yeah, and SARS, right?
And SARS, yeah. So it's
so what's SARS? What's SARS?
SARS, it's an anti-crime unit here in Nigeria.
Anti-robbery.
Anti-robbery unit here in Nigeria.
Oh, okay.
So
please be safe. Please be safe out there, okay?
We're proud of you. Keep doing what you're doing.
And Tim, I hope your family back home is safe.
Okay. We're in Ghana, but yeah.
Okay. I think I like you better because you're from Ghana. But anyway. So
no, I missed it. Why do you need a physical exam? Did you get injured?
No, so my neck, what do you call it? My neck froze up. It snapped. It like froze up one snap.
He has a bad pillow. He needs to get a better one. And
No,
he had
I
a
think it's more. I think it's also because I wasn't moving around as I used to, so I started working out again.
Okay, yeah. Okay, guys, so this is chapter 7, Ensemble Learning in Random Forests. And I hope, Tima, you crashed that exam for the decision trees, even if you were not there, because you read a little bit about it. And so this ensemble is taking advantage of the wisdom of the crowd. So it's not the first time you'll hear about ensemble. I mean, it's not the last time you'll hear about ensemble models, because people who win like the Kaggle challenges really rely on ensemble modeling. And so there's never really a best model, especially for classification tasks. You know, guys, that I like to repeat a lot. So classification tasks is like pneumothorax, non-pneumothorax. And if you look at those challenges, it's most of the time that they come up with different models and then ensemble at the end to make a winning submission. And so, so if you aggregate the predictions of a group of predictors, for example, classifiers or regressors, remember, are numeric, like the housing prices, you'll often get better predictions than with the best individual predictor. And so this group of predictors is called an ensemble, and this technique is called ensemble learning. And so a random forest, last time we talked about a decision tree. Toby did a fantastic job of talking about how they branch and the decisions using the petal length and width. And so here is that you train a group of decision tree classifiers, each on a random set of their training set, and then you obtain those predictions and predict the class that gets the most votes. So random forest, very good for figuring out feature importance. And we've talked about feature importance, which is like, if you have 50 things that could be important, what's the most important? So random forest is a very good technique. In fact, when I review papers, I usually, when you say you're using random forest and you're not really trying to say, this is the feature importance, then for me, I'm like, you didn't understand the technique and you should change that. And so the methods for ensembling are bagging, boosting, and stacking, and that's what I'm gonna go through. And so there's this idea of a hard and vote and soft voting. And it's interesting because right now we are in the voting season. If you're eligible, I hope you voted. And you can see that what we have here, if you trained different classifiers, so we've talked about logistic regression, this would be a prediction of classes, the support vector machines classifier, and a random forest classifier, and any other for classifier on your data set, and each one is achieving around an 80% accuracy. So what do you do with this? You come in and say, I'm going to pick all the predictions of all those different classifiers, and then aggregate the predictors and say this is the majority vote. So here it's, if you think about hard voting, it's like yes or no. You don't care that maybe I voted 90% for one person and 70% for another person. You can see that if the class is 1, 1, 1, and so your output really here, whatever is normalizing your output for your prediction has to have an output of a binary classification or just a quantifiable classification, then that's hard voting, where you pick who's the best winner. And so hard voting, you just use a simple majority vote for accuracy. And so, and ultimately, you still get the best classifier in the ensemble. Even if each classifier had lower predictions, the ultimate one here usually is a better performance. So like 90% if everything was 80%. But to get this, you have to remember one thing, that you have to have sufficient enough of number of weak learners, and they have to be diverse. If you're contaminating a lot of your data set, then you're not going to get improved performance. So that's hard voting. I'm just gonna keep going. You can interrupt me, add anything, whatever time. And so they introduced this concept of law of large numbers. And so it's this coin example where so suppose you have a slightly biased coin that has a 51% chance of getting heads and obviously 49% of tails. And if you toss it 1,000 times, so if you have a 51 chance of getting heads, you get 510 heads and 490 tails. And so you get a majority of heads. But if you if you do the probability, I'm not gonna do the math now, you'll see after 1,000 tosses, that the probability of getting a majority of heads moves up to 75%. And so the more you toss the coin, the higher the probability. So if you move from 1,000 to 10,000, the probability climbs over 97%. And so this is the law of large numbers. So as you keep tossing the coin, the ratio of heads gets closer and closer to the probability of heads. And so this figure is showing that you have multiple number of joint courses, and you can see as the number increases, the ratio of heads starts to approach the 51%. So if you look at the ends here and the lines, they come close to each other, although they started off differently. And so, so this is the law of large numbers, and it's just saying why you end up with these different classifiers, like in the previous image, but you still end up with a higher performance model. And so, like I mentioned, that ensemble models, you have to make sure that they work best when the predictors are independent from each other as possible. And so one way to get diverse classifiers is to use very different algorithms. And so this increases the chance that they will make very different type of errors. And so ultimately, the wisdom of the crowds, you improve the ensemble's accuracy. So this has now become very familiar, right? Everything we're always importing from scikit-learn. We remember this, it was support vector SVC, support vector components? Yeah. And classifier, sorry. At a moment there, thanks. And so we also know that we have logistic regression here. And we know that voting is a type of an ensemble. And we've talked about random forest, how you select from random subsets, trees on random subsets of data, and then pick the best performing one, that's an ensemble model. We know that this is the way we call classifiers. This is just the way scikit-learn does it, and this is how the book does it. So log classifier is equals to logistic regression, random classifier, random forest classifier, and SVM, SVC classifier. And so you can see we're creating a voting classifier here, and we are putting estimators as the different types of random models. These were like the three big things at the top. So SVC, RF, and LR. And we're using a hard type of voting, which I explained. It just takes a majority of the vote, and then we are fitting on the X and Y train. And remember, X is what you need to learn, and Y are the predictions. And so if you look at this and you import accuracy score, we've used this in the past for classification tasks. And you can see, could you show me what all this is saying for this classifying all of these fits the Y train and X train and Y train data set, and then generate a predictor for Y on the X data set. And then, you remember that we can get the accuracy score. And so we're just show me the classifier for logistic regression, which ends up to be 0.86, at the random forest, which ends up to be 0.89, and SVM, which ends up to be 0.88. But if you look at when you use the hard voting, then you end up with a higher voting classifier, which is 0.908. So this hard versus soft voting, when I was reading, I just put these slides here because maybe someone else also didn't understand it initially. So suppose you have this probability, 0.45, 0.45, and 0.9. So the hard voting, you just give one of three, one vote in favor and two against. So it would classify as negative because you have these two, because you're just taking the majority. And remember, most of this, we just cut the probability at 0.5. And so soft voting would give you an average. So you have to add all these 0.9, it will be 1.8 divided by 3, so you get 0.6 and would be a positive. So you can see how the difference in hard and soft voting occurs. So soft voting requires you to have a probability because it's like an average. And so it takes into account how certain each voter is rather than the binary input from the voter. So in summary, hard voting is where a model is selected from an ensemble to make the final prediction by a simple majority vote for accuracy. But soft voting can only be done when all your classifiers can calculate probabilities for the outcomes. And it arrives at the best result by averaging out the probabilities created by individual algorithms. So how do we change that? Remember, this is the code that I went through for the last ones. These are the various estimators, and you just have to change voting is equals to soft. Okay. I'm moving on to bagging and pasting. Any questions? Okay. Bagging and pasting. What I would have put here is a shopping bag, really. So remember, we have different classifiers here. Okay. And we've said that one way to get a diverse set of classifiers is to use very different training algorithms. But the other approach, so this is what we did, and we did the voting system. But the other approach is you're using the same type of predictor, but you're training them on random subsets of the data. Okay, one, you're changing the different algorithms, and one, you're just splitting that the same algorithm is seeing different. So for example, if you use a SVM classifier, you're just using the same type of data set, only that same algorithm, but different portions of the data set. So it's almost like different aisle in a supermarket. And so so the idea of bagging and pasting is that when sampling is performed with replacement, this is called as bagging, and this is short for bootstrap aggregating. So you're putting, let's say you have this 20, 20, 20, because your data set has 80 samples. If so it won't be like very separate. It's going to be that you pick this 20 from the 80 data set, you train, and then you put them back into the bigger bucket, and then you pick another 20. So because you're picking them randomly, then you hope that you're going to have differences, and that brings a new concept that I'm going to talk about right now. And so just remember, if you're randomly sampling but you're replacing the samples, then that's bootstrap. But if you're not replacing the sample, if you have a bucket with water, and once you fetch it out, you're not putting it back into the water, then that's called pasting. And so you can see, again, this is starting to make sense, right? We know that this is an ensemble because this is a bagging classifier model. Same thing, you have, what was important here is the number of estimators, maximum samples, and bootstrap, it's true, and the number of jobs. So what do all these things mean? Number one is that once all predictors are trained, the ensemble can make a prediction for a new instance by simply aggregating the predictions of all predictors. And so this is like, we use a mode. Remember there's mode median, and this works like a hard classifier, or you can use average for regression. And so there's this concept that is introduced here, which is about bias and variance. We talked about it in the beginning of the chapter. And each individual predictor has a higher bias than if it were trained on the original data set. But when you aggregate everything, it reduces this bias and variance. And so if you look at this code, it trains 500 decision tree classifiers, okay? And each of them, remember, you have to use just a portion of the data. Each of them is trained on 100 training instances that are randomly sampled with replacement. So that would be bagging. But if you want to use pasting, then what you would do is that say bootstrap is equals to false. And then the n jobs minus 1, this parameter just tells the number of CPUs that the computer should use. Now, when you're using small data, it doesn't matter, but when you're building a big model, this matters a lot. And so this is just the code to understand how the bagging classifier is working. And so the bagging classifier actually automatically performs soft voting instead of hard voting, as if the base classifier has probabilities. And this is usually the case with decision tree classifiers, as explained by Toby. And so if you look at here, decision tree without bagging, I think we've gotten to a point where we understand this is the Moon's database again. We've gotten to a point to understand where this is. If I just show you this without the labels, you know that this is kind of separating these two lines pretty well, not like joining every dot like in this case. So this is an overfitting model, but with bagging, you can see, true, you always have error, but this doesn't bother us because we know how to understand the errors for regression and classification tasks. And then we know when our model fails, right? So in this case, you'll be doing a confusion matrix that will tell you when there's true positives, false positives, false negatives and true negatives. And then you would calculate the recall and the precision from that. And so, so bootstrapping introduces a bit more diversity in the data set that its predictor is trained on. So bagging ends up with a slightly higher bias than pasting, but the extra diversity also means that the predictors end up being less correlated. So the variance is reduced. Most of this will apply when the model is applied to a new data set that it's not seen before. So there was this concept of out-of-bag evaluation, right? I said you have a bucket of water, you start off with some water. If you're fetching the water, running it through your model and putting it back, this is called bagging, short for bootstrap aggregating. If you're not putting it back, this is called pasting. So let's take this example here of Jeffrey, who's going to be running a marathon and says, well, this is playing tennis though. So, says if it's sunny, hot, high humidity, I'm not playing tennis. The same thing here. And if it's sunny, then yes, I'm gonna play tennis. So I said that when you have bagging, you may have some instances may be sampled several times for a given predictor, while others may not be sampled for any predictor. And so this is where they were saying, like, if you look at some of the example, you may see that 63% of the training instances are sampled on average for each predictor, and the remaining 37% of the training instances are not sampled, and these are called out-of-bag instances. And so, so if you look at this, let's say this is the bootstrap sample that keeps getting sampled. And so this last line here has not been seen by any, sorry, I didn't mean to duplicate that. So if you look at this, then you don't have any, none of the predictors have seen this. And so if you think about what we were talking about with the previous stuff, you always have to do this test and training set. But then in your training data, how you build a model is by creating you can do the cross validation. Guys, if I'm saying something that's not familiar now, please stop me. This word should start to get familiar now because you've been using them. And you're just saying, okay, I have this sample. It's not my test. I've not seen my test. But I need to know how I'm going to penalize my model so that it works well. So this out-of-bag sample can be used for validation, which is a power of using this technique of bagging, because now you already have this as a validation data set. Okay, so this yes.
So this out-of-bag, he says if you use enough estimators, like for example, if you're trying to grow a random forest with like a 500 estimators, is that big enough to out of bag for one estimator be in bag for other estimators?
I think they said that it's not the same out of bag for every estimator. So like the 37% will be different for every estimator, right? Because
so my understanding was he's saying that when the number of estimators goes up, then the probability of one of the estimators at some point is able to train on every single instance goes up.
Yes.
And then so then this out-of-bagging only works if we are using limited number of estimators. But for example, I'm not sure if 500 is considered low or high, or apparently this is not high enough. So he's using this out-of-bag.
So I don't know the actual number, but of that, but of one, I would say that you shouldn't use, because what this is doing is creating 500 decision trees, right, on your data set, right? So you can imagine that's quite a bit of math, but I don't know, I can't tell you that it's 1,000 or 5,000, but maybe one of us can.
So a question about that, sorry. So this is the same thing, kind of along those same lines, I guess, the out-of-bagging thing. So I was trying to understand, I guess, as you just mentioned, it's kind of similar to that k-fold cross-validation in a way. But so is the out-of-bag being used as a validating data set for the same set that it is coming from, or is it
Yes.
used for all the other one? Okay.
Yes. So let me recap that. When you split your machine learning data set, you have your train and your test, right? We all agree test, we never show it at all. We never use it for training. But remember the gradient descent. If you're coming from the top of the mountain and coming to the bottom, then you're saying, gee, I need to figure out how am I going to, what routes have been used. And so you have to keep going up and up. Those are the entropies, right? How many times you have to keep going up the mountain to figure out, okay, what's the best way? I want to avoid the way with the lion, and I want to avoid with something else, okay? And so if you're thinking about that, the way you give feedback to your model that it's on the correct way, which is the loss function, right? And if we remember, we said we have early stopping, which is discussed in this chapter, which is where you're looking at how much loss is working on your validation. And if the loss is not getting better, then you don't have to keep using your GPUs to keep running the code. You need to stop, because you either need to change your model or you need to look, and this is the best that you can get. And if you look at also the validation curves, and so this is a very important point of just having some data set that gives feedback on your model if it's on the right track. And so this out of bag evaluation, because it's a data set that's not being used for training, is how this bagging mechanism, you can use this as an opportunity to do your validation. Remember, validation is different from testing, okay? So, and the way to do that is by putting an OOB score is equals to true. So you can see that if this happens this way, then this becomes 91%, okay? And the bagging classifier, so according to this out of bag distribution evaluation, this bagging classifier is likely to achieve about 90.1% accuracy on the test set. So now if you come in here and you do the actual prediction on your test set, you can see the accuracy score is around 91%. So close, and you can see how the utility of the out of bag. So, so this is the way, we've seen that this is how scikit-learn likes it, right? So you have a classifier, and if you just do dot and you do out of bag decision function, you can use this function to tell you for each training instance, right? You're always training your model many times. So like in this case, you're going maybe 500 times. And so in this case, you can use this to tell you what's the probabilities for each training instance. So for example, here, it's estimating that the first training instance will have a 68.25% probability of belonging to the positive class and 31.75% probability of belonging to the negative class. It's just showing you how to use this function in scikit-learn. So then there was this concept of random patches and random subspaces. And honestly, the first time I read it, I don't think I understood it well. And so this is still part of bagging. And so the bagging class supports sampling the features. And so sampling remember, bagging is still taking things out and putting them back. And so this sampling is controlled by two hyperparameters, the max features and the bootstrap features. So this one and the max features. And so they work, they work as usual, but what they've been used for here is for feature sampling instead of instance sampling. And so the difference is that the random patches will sample both the training instances as well as the features, but the random subspaces keeps all instances but samples the features. I don't know if anyone has a better explanation. I spent quite some time trying to look for a good explanation, but I only found that if you're sampling both training and features, then this is the random patches. If you're keeping all training instances and you keep those by setting bootstrap usually you'd say that bootstrap is equal to false and maximum sample is 1, but you're only sampling the instance, the features only, then this is a random subspaces. Almira?
I think you just explained it exactly as you should. Like, this is like what it is.
Okay. So now random forest. We know that it's an ensemble model. We know that we wanted to create 500 forests, trees, decision trees, and then you specify the maximum leaf nodes. I'm not going to spend too much time on this because Toby did a great job about this. And then your CPU use it, and then you fit, you predict. And then you can see this is the bugging classifier. Here where you're specifying your nodes, estimators, your maximum samples, and bootstrap and the CPU. So in this case, we are using, this code uses all the CPU cores to train a random forest classifier with 500 trees, and each is limited to 16 nodes, because else it's gonna keep going forever. And so remember, random forests are an ensemble of decision trees, and they're generally trained by bagging method. You can use pasting, but typically with the max samples set to the size of the training set, okay? And so this is just showing that you can use this random forest classifier instead of using this bagging classifier, which still is the same, but they said this is more optimized when you use a scikit-learn, okay? And so the random forest algorithm introduces extra randomness when growing trees. And so in searching, instead of searching for the very best feature when splitting a node, for example, how Toby was showing with the decision trees, it searches for the best feature among a random subset of features. And so this is how you get a lot of diversity in the trees, and you subsequently trade a higher bias for a lower variance. And so you have a better overall model, okay? And so extra trees. And so this is the same thing. Again, we talk about bias and more and variance. And so you can use this extra trees classifier, and it's the same to the random forest classifier. And so it's hard to tell in advance whether a random forest classifier will perform better or worse than the extra trees classifier. And the only way to do it is to try both and compare them using cross-validation. And remember, you can use the grid search function of scikit-learn to search for parameters. And so this random extra trees is used for making trees. So when you're growing a tree in a random forest, at each node, only a random subset of the features is considered for splitting. And so it's possible to make trees even more random by using random threshold for each feature rather than searching for the best possible threshold. And that's how the purpose of the extra trees. And you can see, so this is something new. And this is the means data set, where we know that usually in the center here it's a number, and it's just highlighting it more, showing us that these are the pixels with the more information. This is the previous example where we've done the flowers, and we see that the most important feature here should be the petal length, because it's the 44%. And so here what we're trying to say is that you can take advantage of random forests, and the explanation here is that these models tend to be very explainable, because you can just say, hey, show me your random forest classifier, show me my feature importance, and all of a sudden you now can see the relative importance of the features and say, okay, I know that the length and the petal width are more important. And that makes sense from previous when we looked at the tree that Toby drew. And so I'm going to move on to boosting. So we've talked about voting, hard and soft voting, bagging and pasting, and some extra things about random forests, including extra trees and how to get feature importance. And so boosting, you have many methods, EDA Boost, gradient boost, and boosting is almost like boosting a score or boosting a signal for cellular network, where you have you pick any ensemble, it can refer to any ensemble model, and what you want is to combine several weak learners to make a strong learner. But the difference here is that we have to train, remember all the rest, we're either splitting the data into small components or splitting the data, training different classifiers and then averaging them. But here what we're doing is we're going to train the predictors sequentially, so they're in order. In something similar will be like reinforcement learning. So you start here, you get to learn, you figure out where the weakness is, you put it into the next one, and you get to learn. So it has to, this sequential nature is what is important about boosting. And so the algorithm trains a base classifier, like a decision tree, and then uses it to make predictions on the training set. And then the algorithm then increases the relative weight of misclassified training sets, trains a second classifier, uses updated weights again, and makes the prediction on the training set. Remember, guys, I'm not talking about the test set. This is just within the training set, and keeps updating the instances, so and so on. And so they give this as an example of just the multiple times that it keeps working and getting into a classifier. So this is an SVM classifier. The first classifier gets many instances wrong, and then their weights are boosted. And then the second classifier, keeps getting better and better, because that's how it works. And so if you have to think about this sequential learning technique, is that it cannot be parallelized. So you use quite a bit of compute, because it can only be trained after training has been completed for the previous predictor. And the math, which Judy's never good at as explaining, but what I want to say is that you start off with a base classifier, you're putting in some weight, and then you're updating the weight because of this sequential learning. I really personally don't want to spend too much time on this unless anyone feels that they won't. Let me not rephrase that. Does anyone want to explain this math? Really, not takers?
Yeah, Judy, I don't think you want me to explain that math.
I'm not going to go over the math, but one thing that the sequential training reminds me of is the mini batch.
Yep.
Mm-hmm.
The way that, so actually the whole thing, it looks like the whole ensemble. I'm just thinking of like in mini batches, we are improving the model as we get the training sets. Now we are like training the whole model on like mini batches of samples or mini batches of instances, and then like aggregating their results. And apparently this one works better than the other one, or?
Yes. So it's like mini batches, but you're dynamically changing the component of the mini batch, the next mini batch, right? Because remember, you're saying, look, this is a weak learner, it performed poorly on, let's say, black patients. So your next batch, you're going to increase the ratio of black patients so that the next learner learns better on that information. So remember, the other ones, you'd split all your data set at one go and decide, gee, this is random. You can do the stratified k-fold sampling. But once that's done, then you come back and you're just running the data. You're not thinking about what you're feeding into the next batch. But this one, you're thinking about how am I going to compose my next data set to be representative, and because I know how the previous classifier worked. Okay. And so, there's this thing about in the EDA Boost, which is, so instead of a decision tree, the EDA Boost uses a decision stamp, which is a decision tree with a maximum depth of 1. So they're just like, the way I thought about this is like, some trees are tall, some are small, and so the EDA Boost uses very short trios. And so it simply computes the predictions of all the weights and weighs them using the predictors of this function. I really don't want to go into that because Toby, Chima, Mezzanine will need to know the math, but they'd rather be taught that by a math teacher more than Judy. But Scikit uses a multi-class version of EDA Boost called the SUM, which is Sagewise additive model using a multi-class exponential loss function. And when you have that numbers can be probabilities, then you do the sum.r. And so this is how you do. We've seen everything else here. And so if your EDA Boost Ensemble is overfitting the data set, then what you need to reduce is you should be changing this parameter, the number of estimators. And guys, you may not realize how much we've learned, but now these things like overfitting, you should be able to draw your validation curves on every task that you get and be like, oh, this is not working well. You're able to look at your metrics and then go back and say, okay, I need to change something in my code, and this is what you would change, okay? And so in this case, we are training an EDA Boost classifier based on 200 decision stamps, and we have a maximum depth of 1. And so every tree is composed of a single node plus 2 leaf nodes, and this is usually the default classifier and then the algorithm. So gradient boosting. So we went through EDA boosting and gradient boosting. All of them are sequential learning, okay? So you can see that this, gradient boosting still works by sequentially adding predictors to an ensemble, but instead of tweaking the instance weights at every iteration like EDA Boost, this method tries to fit the new predictor to the residual errors made by the previous predictor. And so if you look at this, this is a decision tree, regressor, and then with a maximum depth, and then so we train a second one, and then we train a third one. So you're having these trees that are increasing. And now we have an ensemble containing 3 trees. It can make predictions on a new instance by adding up all the predictions of the trees. And so this is, the gradient boosting is working on the predictor itself, but the EDA Boost, you're modifying the sample data that it's going to work upon, okay? So this is like when you're using Ensemble, we know that this is a quadratic model, but you're just showing that as you keep moving, through this sequential learning, and you can see that it almost starts to straighten things up because you're learning and fitting and changing the type of data for that, but you still end up with better classifiers. And with the book format now, you can see that this was very wide, like this red part. And now if you start to look at this, this is more closely in there. It's not lining up on every circle, so it's not overfitting, but this is trying to show the progression with improvement. And so this is just a way that you can also, everything for this SVM and the decision trees and the random forest, you can create a regressor model or you can create a classifier model. And I keep reminding us what those 2 types are, okay? And so, you can see that this is where we start talking about changing in the estimators. Now, this model, is it underfitting or overfitting?
Overfitting.
Overfitting, right? It's trying to draw a line on every circle. And this is a much better model. And you can see what's being changed here is the learning rate and the N estimators, okay? These are the parameters that you'll be changing if you're trying to do this model. So the learning parameter scales the contribution of each tree. So if you set it to a low value like 0.1, you will need more trees in the ensemble to fit the training set, but the predictions will usually generalize better. And so this is a regularization technique called shrinkage. And so, so this one doesn't have enough trees to fit the training set, while this one has too many trees and overfits the training set. So I talked briefly about early stopping, and what this is trying to do, we see that we have some metrics here. We've train, test, split. This is what we talked about this very early in the course. And now we've built a gradient. Remember, we talked about EDA boosting and a gradient boosting, the maximum depth and estimator, and you fit the model. And then now you look at errors. And so here you see that if you're using, if in order to find the optimum number of trees, you can use the early stopping, and you can use this staged predict method. And what it does is that it returns an iterator over every prediction made by the ensemble at each stage of training. And so, so in this case, we have a model with 120 trees, and it measures the validation error at every stage of training to find the optimum number of trees. And then finally, retrains, you can see the N estimators, right? So we started here, and what it's doing here is like saying, why don't you show me what's the best n estimator, what's the best number of trees, and then in the best, you fit in this variable, which is you got here by using this staged predict. So very cool trick here. And so same thing, trying to show that you're looking at where your error is. And here, when you start, your error is not changing, then you should stop your training. And so you realize, okay, maybe my number of trees is 56 in this case. And so now you draw a model here using n estimators is equals to 56 instead of n estimators is equals to 200. And so there's also another way. We talked about this, this technique of using staged predict, but the other way is using the warm start. And you can use this specifically. This is an example that's showing regressor. And what it does is that it stops early. Instead of training a large number of trees first and then looking back to find the optimum number, which is what the staged predict is, you can set the warm start is equals to true, which makes scikit-learn keep existing trees when the fit method is called, allowing incremental training. And so in this case, if the error keeps going up above 5, then you should stop because it's not improved over 5 iterations. So there are a few things that were randomly mentioned there. Stochastic gradient boosting. And this is, so we talked about EDA boosting. We're changing the batch that the model sees next. And then the gradient boosting, we're changing the algorithm itself and the losses. And then stochastic gradient boosting is we are training each ensemble on a subset of the training set. And so you can see variants. You can subsample rows before creating each tree, or you can subsample columns before creating each tree, or columns before each split. And so in this case, the gradient boosting regressor, is this, you're using this subsample parameter, and this parameter, it specifies the fraction of the training instances to be used for training each tree. So for example, if you say the subsample is 0.25, then each tree is trained on 25% of the training instances, and these are selected randomly. And so, it speeds up training considerably, and you can see, yeah, that's it. Then it's not implemented in scikit-learn, that's why there's no code for it. So then there's this XG boost, and this is what you have to know, because this is what people win Kaggle competitions on, okay? And you can see you're just calling an XG boost, regressor, train, and predict, and then you fit it. And so here, instead of making hard yes and no decisions at the leaf nodes, remember that was very common when Toby was explaining this, the XG boost assigns positive and negative values to every decision made. And so all trees are weak learners and provide a decision slightly better than a random guess. So I couldn't find a much more detailed difference apart from that. But if you're trying to think, what should I use in terms of the boosting, I think you should check out the XG boost because it has better performance. And so this idea of stacking, is based on a simple idea. So instead of using trivial functions like hard voting and soft voting to aggregate the predictors, you're training a model, which is at this point, to tell you what, so it's in this part, remember in the past you could use code to tell you what you should do. But here what you're saying is that you're training a model that is going to determine what's the best, what aggregates this output, and each of the bottom, so like each of these bottom predictors predicts different value, and the final predictor, which is the model you're creating, or also known as a meta learner, and this is stacking, takes the predictions of these inputs and then makes the final prediction. So that it's just the way you're organizing this. Remember, we talked about this level is about soft and hard voting, but this is because you're using different data sets. But when you're using the same data set, you can either use boosting or pasting. And if you want to subsample them differently, then and train them sequentially, that's when you get to the boosting techniques. Okay, and so this blender does that. And so now to train the blender, a common approach is to have a holdout subset of the data. And so you do this where you train your 3 things, get your prediction, get the blender, and then now you bring your blender on your subset 2, and now it does predictions and uses the prediction to generate what's your final output. So that's all that it's showing from this. And so that's how I understood the chapter. These were some resources that I found. I'll obviously put this on the channel. Cargo, if this fantastic person here made a tutorial on Ensemble Learning. The good thing about Cargo, you just need a browser. You don't need to install anything. So I'd encourage you to go maybe and read through this and just see, oh, okay, I can understand what's being said. And then this was also another resource from Kaggle on an Ensemble Learning. You can see what they're trying to show you: maximum voting, averaging, weighted averaging, stacking, blending, bagging, boosting. All these things now kind of, at least when the words are said there, you should be able to read them and just honestly click through their stuff. Most importantly, and I emphasized this last time when I said we have to do a little bit of outreach and building your content. This is something I actually got it through Twitter. I know Sebastian, I don't know him in person, I follow him on Twitter, and he teaches this machine learning course. And guess what he has? It's actually ongoing right now, and he's posting his videos. These are very short. I just actually play them as on my way to work. Whatever I hear. Whatever I don't hear, I don't understand. But you can see that this segment, if you have some time, you can just go and honestly, he's done even for previous ones. This morning I had to drive somewhere and I listened to this one, and he just said, hardly anyone uses SVM, you know, but I'm curious to see what the others will do. That's it, folks. Any comments?
That was a good presentation.
Thank you.
Right, thank you.
Clarify, yeah.
That was great.
Thank you.
So stop the recording.